Hello guys, welcome to my YouTube channel Control System Engineering. I Professor Darshan Thakur is going to explain one of the most interesting article of this control system phenomena, that is nothing but Bode plot, right? So as we are very much aware of this thing, this Bode plot is nothing but what? The simplest definition of this Bode plot is nothing but it is the graphical representation of this given transfer function, right? So we will go through this Bode plot technique with this basic example, in which, as you can see, the question is like this: for the unity feedback control system whose open loop transfer function g of s equals to 10 over s into s plus 1 into s plus 5. So our objective is to, as you can see, sketch the Bode plot and determine these two corresponding parameters of this Bode plot. By taking into account these two parameters, we can define the stability of that given system, means whether that given system is stable, unstable, marginally stable, etc. like this, right? So first of all, what we need to do while plotting this Bode plot, we need to follow certain design steps, right? So in this step number 1, basically what we need to do, as you can see, we are having this OLTF with us. OLTF stands for open loop transfer function, right? So first of all, we need to write this OLTF in standard time constant form. So that will be our step number 1. That is nothing but to convert this given OLTF in standard time constant form, like this, time constant form. So for that purpose, one more time we need to write this given OLTF, open loop transfer function, which equals to g of s equals to 10 over s into standard time constant form, means as far as this denominator polynomial is concerned, see, the coefficients of these denominator polynomials are s into s plus 1. So standard time constant form means it is always written in 1 plus s form, right? So this s plus 1, that can be rewrite as a 1 plus s. Similarly, this s plus 5, how it is to be rewrite? This 5 can be treated as a common term in order to put this given expression in 1 plus s form. So it will become 1 plus s over 5, right? So in this way, again, this g of s equals to what? 5 to the 10, so it will become 2 divided by s into 1 plus s into 1 plus s over 5, right? So in this way, that given OLTF is to be rewrite in that time constant form. After that, as we know, this is the graphical representation, means this Bode plot is basically divided into two different kinds of plot, right? These two plots are nothing but first one is nothing but the magnitude plot, and second one is nothing but the phase angle plot. So from magnitude and phase angle point of view, what we need to do, we need to convert this s domain expression into the frequency domain. So here this s is being replaced by this j of omega. So as a result of replacement, this g of j omega equals to 2 upon this s is being replaced by j omega, 1 plus j omega into 1 plus j omega upon 5, right? So this is how our OLTF will look like in this frequency domain representation. G of j omega equals to 2 upon j omega into 1 plus j omega into 1 plus j omega upon 5, right? So immediately after that, we need to follow the step number 2 as far as this Bode plot is concerned. So in that step number 2 is nothing but we need to determine how many number of poles, zeros, and how many constant terms we do have in this OLTF in case of frequency domain, when it is being represented in terms of frequency domain, right? So in this way, So in step number 2, we need to determine how many number of factors we are having in this given transfer function. So one more time, I will write this statement here: g of j omega equals to, already it is being tabulated, 2 divided by j omega into 1 plus, sorry, it is 1 plus j omega into 1 plus j omega over 5, right? So this is the desired statement of this open loop transfer function. So in that step 2, we need to determine how many number of factors we are having, right, in this open loop transfer function. So factor in the sense how many constants we are having, how many zeros and how many poles we are having, right? So as far as zeros and poles are concerned, these are the two desired frequencies of this transfer function, which is to be determined when we equate this numerator, this denominator polynomial equals to 0. This will give you the number of poles, and when we equate the numerator polynomial equals to 0, this will give you number of zeros, right? So here we don't have any term, S domain term or the j omega term, which is being located at this numerator polynomial. So we are not having any zeros as far as the poles are concerned. So there are 3 identical terms belongs to j omega in its denominator, means there are 3 poles we are having with us, right? So one by one we will enlist all these factors. So the first factor is nothing but this constant term 2, right? So as I told you earlier, this Bode plot is being divided into 2 different plots, right? First one is nothing but the magnitude plot, right? And second one is nothing but the phase angle plot, right? So from this magnitude plot point of view, what we need to do, ultimately we need to determine the desired magnitude of this constant factor, right? So which is given by the standard notation 20 log of k, right, where k is nothing but the constant factor whose value is exactly equals to 2. So when we determine this quantity with the help of this scientific calculator, it is 20 log k equals to 2. So it is 6.02 decibel. 6.02, this is the unit of this magnitude, decibel, belongs to this first factor, right? Now the second factor is nothing but this pole which is present at this origin. So whenever we are having pole or zero which is present at that origin, so we are not having any corner frequency belongs to this factor, right? So immediately we need to consider the third factor whose value is 1 divided by 1 plus j omega, right? Now here we need to determine the omega c, corner frequency of this factor, right? When this factor is being represented is in terms of S domain. So how it is to be, right? It will become 1 divided by 1 plus j omega. S is being replaced by j omega. So it is the standard time constant form. It is 1 plus S into t, where t equals to how much? 1, right? And this frequency is nothing but, it is always reciprocal of time, right? So 1 by 1, obviously its corner frequency will be what? 1 radian per second. Omega c 1, that can be treated as it belongs to this factor, right? Which factor? 1 divided by 1 plus j omega. When we consider the fourth factor whose value is 1 divided by 1 plus j omega upon 5. When we consider this factor in terms of S domain, so it will become 1 divided by 1 plus what it is? J omega is being replaced by S. So 1 divided by 1 plus S by 5, where t equals to what? It is 1 over 5. So the corner frequency omega c2 is the reciprocal of time. So it is 1 divided by 1 upon 5. So obviously which will become 5 radian per second, right? So in this way, in this step 2, we need to enlist the different factors along with their magnitude and corner frequencies. The magnitude for this constant term is 6.02 dB. This is the pole which is present at that origin, so obviously it is not being considered for this corner frequency. The next two poles whose corner frequencies are 1 radian per second and 5 radian per second, because frequency is the reciprocal of time. Then the the most important part of this Bode plot calculation as far as this magnitude plot is concerned, this is the third step, right? So in that third step, we need to prepare one kind of table to determine or to plot the magnitude plot, right? So as far as these tabular calculations are concerned, so first of all we need to note down how many number of particulars we need to include in this table, right? So accordingly, the first particular will be what? We need to consider the desired value of factor here, right? So the first particular will be factor. Second particular will be the corner frequency of that factor. Third particular will be the initial slope, or simply we can call it as a slope of that factor. Then next one is resultant slope, or the final slope of that factor. The remaining 2 points are, this is the starting point of that factor and end point of that factor, and here I will write the serial number, right? Like we are having how many factors as far as the previous step is concerned, in which we had enlisted the total number of factor in this open loop transfer function. So as we are having the 4 factors, one by one we need to write these factors here in this table. First factor is constant term 2, second factor is the pole which is present at that origin, 1 over j omega. Third factor is nothing but 1 divided by 1 plus j omega. Fourth factor is nothing but 1 divided by 1 plus j omega over 5, right? So one by one we need to include all these factors. So as we are having 4 serial heads, out of that 4, first one is this constant term, so it has nothing to do with this corner frequency, right? Again we don't have the initial slope, its resultant slope already it is being tabulated. How much it is? It is 6.02 dB by using this formula 20 log k. So it will become 6.02 dB, right? Whose starting point, as it is plotted on the semi-log paper, right? Whose vertical axis is just similar to the normal log paper. It is the linear scale, but as far as the horizontal axis is concerned, that is the logarithmic scale, because within that horizontal axis this frequency is to be plotted, right? So whose starting point is arbitrary, we can select it as a 0.1, which always passes through this infinity. The end point will be the infinity. Second factor is nothing but the pole which is present at that origin, it is 1 over j omega, right? Whose corner frequency, it has nothing to do with this corner frequency. Whose initial slope, it is minus 20 dB per decade, right? Decade means 10 division, as it is being plotted within that semi-log paper, so it is being considered as a minus 20 dB per decade. That will be the final slope, minus 20 dB per decade, right? And the starting point of this second factor is just similar to the starting point of this first factor, which starts at this 0.1 and ends at this infinity. So the starting factor will be 0.1. Laterly we will decide the end point of this second factor. Before deciding the end point of the second factor, let us consider the third factor, which exactly equals to, it is 1 divided by 1 plus j omega, right? Whose corner frequency already it is being tabulated, it is 1 radian per second for 1 divided by 1 plus j omega. Corner frequency is 1 radian per second, which is written here. Whose initial slope is again minus 20 dB per decade, and its final slope will be at, already we are having minus 20, so minus it will become minus 40 dB per decade, right? Now to decide the starting point of this third factor whose value is 1 divided by 1 plus j omega, right? The starting factor itself is its corner frequency. The corner frequency for this third factor is how much? It is 1 radian per second. So that will be the starting point, 1, right? If the starting point for this third factor is 1 radian per second, so obviously that will be the ending point for this previous factor, right? So this 1 over j omega, whose resultant gain is minus 20 dB per decade, whose starting point is 0.1 and ending point is how much here? 1, right? In this way. Now similarly, before deciding the ending point of this third factor whose value is 1 divided by 1 plus j omega, let us consider the last factor. It is 1 divided by 1 plus j omega divided by 5, whose corner frequency how much? 5 radian per second, whose initial slope is minus 20 dB per decade, and whose final slope will be this minus 20 minus 40, it will become minus 60 dB per decade, and its starting point is nothing but what? Its corner frequency. The corner frequency for this factor is 5 radian per second, so this will be 5, right? If the starting point is 5, so obviously the end point for this previous factor will be 5. So in this way it is being decided ki the ending point for this factor number 3 will be 5 radian per second, and the end point for this factor will be, it will passes towards the infinity, right? So this is the step number 3 in order to draw the magnitude plot, right? Similarly, after that, the step number 4 is being exclusively defined for the phase angle plot. So how this phase angle to be determined? For that purpose, one more time here I will write this open loop transfer function g of j omega equals to 2 over j omega into 1 plus j omega into 1 plus j omega upon 5, right? So what it is the phase angle of g of j omega. So obviously we don't have any phase angle belongs to this constant term. It is 0 degree as far as its denominator polynomial is concerned. So there are 3 terms: 1 over j omega, 1 over 1 plus j omega, 1 over 1 plus j omega divided by 5, right? So phase angle, whenever that particular frequency is written in this form, a plus ib, right? So its phase angle will be what? Always you need to remember that tan inverse b by a. This is the real and this is the imaginary part, right? Now as you can see, we don't have any imaginary part, so it will become tan inverse of b by a, right? So j omega obviously imaginary, so b by a, so tan inverse of omega upon a equals to its real part equals to 0, so something omega upon 0, so it is tan inverse of infinity, right? For the first factor, right? Second factor, what it is 1 plus j omega, so it is tan inverse of b by a. Its real part is 1 and imaginary part is also 1, so it will become tan inverse of omega by 1, means tan inverse of omega. As far as the third factor is concerned, or it is the factor number 4 but pole number 3, right? So its desired value is what? It is 1 divided by 1 plus j omega upon 5, a plus ib, right? A equals to 1, its imaginary part omega, right? Again it is imaginary part will become what? Omega upon 5, so this will become tan inverse of b by a, right? Tan inverse of b by a. Here b equals to what? It is 1 over 5 and a equals to 1, so it will become tan inverse of omega divided by 5, right? When we rearrange all this term, when this denominator is being shifted to the numerator, so it will become minus of tan inverse infinity minus of tan inverse of omega minus of tan inverse of omega upon 5, right? So its phase angle will become g of j omega equals to phase angle g of j omega tan inverse of infinity means it is minus 90 degree minus tan inverse of omega minus tan inverse of omega divided by 5. This is the desired value for phase angle, right? Then immediately what we need to do for this for this phase angle plot, we need to draw one more table here like this. For the different values of this, what we can say that omega, right? For different values of omega, right? This omega starts from the starting point is what? It is 0.1. Then after that it will be 0.5 radian per second, then 1 radian per second, then 5 radian per second, 10 radian per second, 50 radian per second, 100 radian per second, 500 radian per second, and finally 1000 radian per second. So here we need to consider all these different frequencies, and for all these different frequencies we need to determine the desired phase angle, right? So in this way, okay, so this will be the step number 4, which will tell us how to determine the phase angle for phase angle plot. So phase angle of g omega, already it is being tabulated, minus 90 minus tan inverse of omega minus tan inverse of omega divided by 5, right? So this phase angle is to be tabulated for different values of this omega, right? So from our magnitude plot table, we are coming on to this conclusion कि our plot starts at this initial frequency, that is nothing but what? It is 0.1 radian per second. Then similarly the next iteration will be taken at 0.5 radian per second. Then after that, as it is the logarithmic scale, so 1 radian per second, then after that 10 radian per second, 100 radian per second, 500 radian per second, and lastly 1000 radian per second. So we need to consider all different values of omega to determine the phase angle. So the desired value of this omega is to be substituted in this expression, right? So with the help of this scientific calculator, when initially omega equals to how much? 0.1, at that time by using this expression, phase angle will become what? It is minus 90 minus tan inverse of 0.5 minus tan inverse of 0.1 upon 5. So it will become 96.85 minus 96.85 degree, right? Similarly, when we iterate for omega equals to 0.5, at that time it is minus 90 minus tan inverse of 0.5 minus tan inverse of 0.5 divided by 5. So it will become minus 121.87 minus 121.87 degree. Similarly for 1 it will become minus 146.30 degree. When omega equals to 10, it will become minus 237.72. For omega equals to 100, it will become minus 266. These values are being already tabulated, right? When omega equals to 500, minus 269.31, and when omega equals to 1000, it will become minus 269.65. So in this way, for this phase angle plot, the desired phase angle is to be tabulated with this expression by iterating the different values of omega, right? So that will be the step number 4, right? Immediately after that, what we need to do, the most important part of this body plot sketching. Now with the help of the semi-log paper, we need to plot that body plot. Okay, so the last step is, as you can see, this is the semi-log paper. As I told you earlier, whose vertical axis is just similar to the graph paper, it is the linear axis, right? But as far as this horizontal axis is concerned, as you can see, this is the horizontal axis, this is the logarithmic scale, right? As you can see, we are having the different particulars belongs to this frequency starting from this 1 to 9. This entire portion can be considered as a one decade, right? Again, 1 to 9 means that can be treated as a second decade, third decade, like this. So here on this horizontal axis, the frequency is being taken into account, and on this vertical axis, the magnitude as well as phase angle is to be taken into account, right? So in this semi-log paper, we need to draw the two different plots, right? First one is nothing but the magnitude plot, and second one is nothing but the phase angle plot, right? So first we will draw the magnitude plot, right? Means we need to draw the reference axis for this magnitude plot, right? So as far as this reference axis is concerned, so here I will draw the reference axis for this magnitude plot. Here I will draw this is the reference axis for magnitude plot. At 0 dB, right? And its linear scale is what? This is this one block can be treated as a 20 dB plus 20 dB plus 40 dB plus 60 dB. Similarly here minus 20 minus 40, like this, right? So the reference axis is to be plotted on this 0 dB, and the linear scale varies from plus 60 degree, sorry, plus 60 dB to the minus 20 dB, right? Now in order to draw this magnitude plot, what we need to do, we need to consider the desired table, which is already been tabulated in this step number 3, right? This is the table for which plot? Magnitude plot. So as you can see, the first factor here we need to consider, so at which desired decibel we need to plot this factor at 6.02 dB, right? Which will start from this point 1 and ends at this infinity. The starting point is how much here? 0.1. So accordingly, see, as far as this semi-log paper is concerned, so whose starting point will be what? Here I will mark. The starting point is 0.1 radian per second, right? So this at this particular frequency, this 9 division stands for 1 decade, so obviously it will become 1 radian per second, right? After that, after leaving that 9 division, it will become here 10 radian per second, right? Again, after leaving these 10 divisions, it will become 100 radian per second, right? Here 1000 and here 10,000, right? So I will mark these frequencies, which frequencies starting from 0.1, 1 radian per second, 10, 100, 500, right, onto this lower axis, right? So this will be the 0.1, right? Here this will be the 1, this will be the 10, 100, this is 1000, and 10,000, like. So first, according to this table, what we need to do, we need to draw one line belongs to this factor whose value is exactly equals to 2, whose desired magnitude is exactly equals to how much here? 6.2 dB, right? As this is the reference axis which is lying at 0 dB, right? In this particular block there are how many division? 1, 2, 3, 4 and 5, right? The entire value of this block is how many decibel? 20 decibel, right? So 20 divided by 5, 5 fours are 20, means the value for each single division is how much here? 4 dB, right? So we need to plot this factor at which, at how much dB? At 6 dB line, right? So this will be the 6 dB line, right, which started at point 1 and ends at that infinity, right? So accordingly, first of all we need to draw this 6 dB line, right? Here the gain is 6 decibel, right? This will be the first factor, right? Then according to this table, the second factor is lying at 1 over j omega, right, whose initial slope is how much? Minus 20, which starts at this point 1, ends at this 1, right? So before considering the remaining three factors, here we need to draw these three tangents of minus 20, minus 40 and minus 60. So our graph starts at this point 1 and the lowest corner frequency how much here? 1 radian per second, right? So by taking into account this fact here, this is the starting point, point 1, right? And the next decade frequency is how much here? It is 1 radian per second. So as I told you earlier, according to this table, the nature of this graph is what? It is minus 20, minus 40 and minus 60, means the nature of that graph is decreasing, right? If it is plus 20, so obviously it is increasing. So due to this negative value, the nature of this slope is in decreasing form, right? So first of all we need to draw these three tangents belongs to minus 20, minus 40 and minus 60, right? So how to draw these three tangents? For that purpose, our starting point is point 1 and the end point is how much here? It is 1 radian per second. This is the plus 20, this is 40 and this is 60, right? So we need to plot these three tangents as a minus 20, minus 40 and minus 60. So we need to join these 2 points. This is the point belongs to this 1 radian per second and this block of this 20 decibel magnitude. So this line indicate when we join these 2 points, minus 20 dB line, right? When we joined these 2 points, the 40 and the 1 radian per second, so this line will become the minus 40 dB line, right? And the third slope is what? According to this table, the third final slope is minus 60 dB per decade. So this entire portion can be treated as a 1 decade. So this will be the minus 60 dB line. Minus 60 dB line, right? So these three for our reference, this is minus 20, this is minus 40 and this is minus 60, right? So one more time, when we consider this table for magnitude plot, so this factor 1 over j omega, whose starting point is how much? 0.1 and which ends at this 1 radian per second, whose resultant slope is exactly equals to minus 20 dB per decade, right? Now how to consider this factor, right? Now in order to consider this factor which is to be drawn or which is to be written after this first factor, whose resultant slope is how much here? 6.02 dB, which is already plotted, right? So this is the 6 dB line, right? Whenever we are considering the remaining factors, so the remaining factors are to be drawn after the 6 dB line, right? Means this 1 over j omega, it is being treated after the 6 dB line. So this 1 over j omega starts at this 0.1 radian per second, ends at this 1 radian per second with this desired slope minus 20 dB per decade. But important thing which we need to note, it will be started after this 6 dB line, right? Because this is the second factor. The first factor is what? The constant value 2, whose magnitude is exactly equals to 6.02 dB. So by default, whenever we are considering the second factor, it is to be plotted after this constant value if we are having any constant into that open loop transfer function. So accordingly, its starting point is what? 0.1, ends at this 1, but it will be plotted after this 6 dB line, right? So how to consider? We need to plot, see, one parallel line belongs to this 20 dB minus 20 dB tangent like this. And we need to highlight this portion, right? So this will be the minus 20 dB per decade, which starts at this 0.1 and end at this 1 radian per second. Then after that, the second factor, third factor, 1 over 1 plus j omega, whose corner frequency is 1, whose resultant slope is minus 20 dB per decade, whose starting point is 1, right? Whose starting point is 1 and whose end point is nothing but what? 5 radian per second, right? Whose desired slope is how much here? Minus 40 dB per decade. So the slope is minus 40 dB per decade. Starting point is 1, ending point is 5, right? So accordingly, it is being drawn after this second factor. So this is the desired line for this second factor, which is lying at this origin. Now see, this is the 1 radian per second, this is 2, 3, 4 and 5. I will highlight this particular frequency by putting one vertical line here, right? This vertical line represents the desired frequency is exactly equals to how much? 5 radian per second, because this is the end point for this factor, right? So it begins with this 1 radian per second, starting point is 1 radian per second, but whose slope is how much here? Minus 40 dB per decade. So we need to plot this parallel line belongs to this minus 40 dB, which starts at this 1 radian per second and ends at this 5 radian per second, which is to be drawn after this first line. So this is in this way. It starts at this 1 radian per second and ends at this 5 radian per second. So we need to highlight this portion, right? So this is the minus 40 dB per decade line, right, for this factor which starts at this 1 and ends at this 5, right? Now when we need to consider the last factor, whose value is 1 divided by 1 plus j omega divided by 5, whose corner frequency is 5, whose desired slope is how much? Minus 60 dB per decade. Starting point is 5 and ending point is infinity, right? So whose slope is how much? Minus 60 dB per decade, and whose starting point is end point of this previous 5 and end point is infinity. So we need to draw one parallel line belongs to this minus 60 dB, which starts at this 5 radian per second, right, and ends at this infinity. So like this, ends at this infinity. So this is the line of minus 60 dB per decade, right? So this is how the magnitude plot is to be drawn. So in this magnitude plot there are 4 factors are to be considered. Out of that 4, first one is the constant whose magnitude is 6 decibel, right? So this is the 6 decibel line, right? Immediately after that, the second factor which is lying at that origin, 1 divided by, it is 1 over j omega, right, whose starting point is how much, 0.1, and ending point is what, 1, and whose slope is minus 20 dB per decade, right? So this is the line which starts at this point 1, ends at this one, and whose slope is how much, minus 20 dB per decade. Second factor whose slope is minus 40 dB per decade, starting point is 1, and whose ending point is 5 radian per second. Third one is what, whose starting point is 5 and it ends at this infinity with this slope minus 60 dB per decade, right? So this is all about the magnitude plot, right? Then immediately after that we need to draw in this remaining portion the phase angle plot, right? So similar to this magnitude plot whose reference axis is lying at 0 dB, so similarly the reference axis for your phase angle plot is always lying at 180 degree, right? So here I will draw the reference angle which is nothing but 180 degree. Here I will draw. It is minus 180 degree. Here it is minus 150, it is minus 120, it is minus 60, so minus 60. So starting from minus 60, minus 180, minus 150, minus 180 in ascending order, it will become minus 210, minus 240, minus 270, minus 300 degree, right? Because this is the second portion, it is the phase angle plot, right? Here as you can see, this one within this one block, the desired range for this phase angle is minus 50, minus 180 means 30 degree, right? So in this one block there are 5 divisions, 1 2 3 4 and 5. So the each division holds the desired value of how much here, 30 divided by 5 means 6 degree. The desired value for each block or each division is 6 degree. Now what we need to do, with the help of this table which is already being tabulated, right, in this step number 4 for phase angle minus 90 degree minus tan inverse of omega minus tan inverse of omega divided by 5, right? So when omega equals to 0.1, the phase angle is how much, minus 96.85, right? So when this is the omega 0.1, so the desired degree is how much, it is minus 96. So here it is 60, it is minus 96, here we are having minus 120, 6 1 the 6, 6 2 the 12, 6 3 the 18. So somewhere we are having this minus 96.85 when omega equals to 0.1. So for this phase angle plot, this is the table which we had calculated for this phase angle plot using this relation. So for different values of this omega, like varies from 0.1, 0.5, 1, 10, 100, 500 and 1000. These are the desired angles. Those are to be tabulated from this relation, right? So we need to consider all these points like this. This will be the 0.1. After that, this will be the 0.5, right? If this is the starting point is 0.1, so this second, third, fourth and line number 5, that will be the desired frequency, which exactly equals to 0.5 here, right? Then the next iteration will be at 1 radian per second, 10 radian per second, 100, 500, lastly 1000, right? So these points are being already marked here. For omega equals to 0.1, the phase angle is 96.85. For omega equals to 0.1, the phase angle will be it is 120 minus 6 here. So somewhere here it is being located. So similarly, this is the second observation point. For omega equals to 0.5, omega equals to 0.5, the phase angle is 121.87. so this is 120, so approximately this is 121. Then for omega equals to 1, phase angle equals to 146.30, right? When omega equals to 1, phase angle is, this is 150 minus 6, so somewhere 146.3. Then for omega equals to 10, it is 237.72. so this is 1. Omega equals to 10, so the desired phase angle is, this is 240 minus 6, 237, it is 237.72. For omega equals to 100, it is 200 minus 266.56. so omega equals to 100. Here we are having minus of 270 minus 6, so obviously this will be minus 266.56. Rounded off value is being taken into account. When omega equals to 500, omega equals to 500, it is 269, and when omega equals to 100, it is 269.65. then immediately after that, freehandly we need to joint all these points like this, right? So this is your phase angle plot and this is your magnitude plot, right? So our objective is what here? Initially we had gone through our objective is we need to determine the stability of that system. So for that purpose, these two parameters we need to determine, this gain margin and phase margin, right? So this gain margin and phase margin is to be tabulated from two different frequencies, gain crossover frequency omega gc and omega pc, that is nothing but phase crossover frequency. So one by one we will try to determine, right? So initially this phase margin is to be tabulated from gain crossover frequency, right? Gain crossover frequency means from this magnitude plot we need to observe at what point this magnitude plot intersect to this 0 dB axis, right? Means the point at which this magnitude equals to 0 degree, right? So this is the desired frequency, right? So we need to determine this particular frequency. If I project this line vertically like this, right? So see, here the desired frequency is 1 radian per second, and after that, as we are having 1 2 3 4 5, right? So here omega crossover frequency will be it is after this one, as we are having the 4 division or approximately 5 division. So the gain crossover frequency it is 1.4 radian per second, right? How much it is? It is 1.4 radian per second. And if I project this frequency towards this magnitude plot like this, right? So this particular distance will give you the phase margin. Now in case of this phase margin, as this each block stands for minus 30 degree, means the value for each division is how much? It is 6 degree, right? So here we are having how many divisions? This is 1 2 3, right? So there are approximately 3.5 divisions we are having. So phase margin equals to 3.5, 3 6 are 30, means it is 34 degree. Phase margin is how much? 34 degree, right? Here phase margin equals to 34 degree. In order to determine phase margin, we have tabulated the gain crossover frequency, means as far as this magnitude plot is concerned, so the point or the desired frequency at which magnitude equals to 0. So this frequency is how much? It is 1.4 radian per second. What this 1.4 radian per second gain crossover frequency to determine the phase margin, right? So this gain crossover frequency is being projected on this magnitude plot and it will intersect here, and so we need to determine that much particular distance in this phase angle plot. Similarly, we need to determine the zero crossover point for this phase angle plot. We need to determine the intersection for this reference axis. So this will be the intersection for this reference axis, that can be call it as a omega pc, phase crossover frequency, right? This is the crossover frequency for this phase angle plot. So we need to determine this particular frequency. So for that purpose, I will project this line upward. So somewhere, see, this arrow indicate omega pc, phase crossover frequency, right? So here up to this point, the frequency is how much? This is 1, this is 0.1, this is 1. Here we are having 10, here we are having 5, 4 3, right? So it is 1, and apart from this one, as we are having 1 2 and 3 division, right? So it will become it is located after this second vertical line, right? After this second vertical line, up to this point, the desired frequency how much? It is 1 radian per second. So here it will become 2 radian per second. So it is 2 point something, right? So each division stands for we can say that 7 to 8 degree. So as a result of this, phase crossover frequency will be, as it is located after this 2 radian per second, it is 2 point, if suppose it is 2.5 radian per second, right? How much it is? 2.5. Now when this is being projected over this magnitude plot, so that much distance is nothing but our gain margin, right? So in case of this gain margin, each block consists of 20 dB, means each division stands for 4 dB. So as we are having, this is first and this is second and 2.5 approximately, right? So 2.5 into 4, right? So 10 dB, right? What it is, this is the gain margin equals to, sorry, 10 decibel. The gain margin is always measured in terms of decibel, so here gain margin equals to 10 decibel. Now as you can see, gain margin equals to 10 decibel means it is a positive value, and phase margin equals to 34 degree means also it is a positive value. So if gain margin and phase margin, if these two values are positive, so that system can be called as a stable system, right? If these two values are zero, so some value is negative, so that system can be called as a unstable system. So in this example, the gain margin is positive and phase margin is also positive, so this system is nothing but the stable system. So this is all about this body plot sketching. So I just hope that you had certain basic ideas regarding this body plots, right? So body plot is nothing but, for that purpose there are two identical plots, one is magnitude and one is phase angle. One table we need to tabulate for this magnitude plot, another table we need to tabulate for this phase angle plot. Then and then we can determine this gain margin as well as phase margin. These two margins are being decided with these two crossover frequency, gain crossover frequency and phase crossover frequency. If these two values are positive, gain margin and phase margin, then that system can be called as a stable system. Okay, thank you.